Okay, so getting started for the night. Welcome all to the April 2023 meeting of the Astronomy Fundamentals Group for TAAA. Tonight, have two presentations. One, which we'll be starting off first, is from Pete Hermes talking about carbon stars. Because I believe you just finished up an observing program on carbon stars.
You did.
Yeah, it was a little while ago, but yeah, and then
Yeah. So
in fact, we've had a couple of members have, and it's kind of a neat thing.
So we'll get to learn more about some of those. And then after that, we will be doing the our astronomer of the month presentation this month on Edward Barnard. And without Doug, sorry, not Doug. I'm so used to Doug presenting. Pete, go ahead whenever you're ready.
Okay, let's pull up the all-important screen.
Sorry, Doug.
No, that's fine.
Everybody see the screen okay?
Yep.
Hey, how about that? This is working out pretty good. And of course, as usual, when I put the people up there, it sort of blocks out my left side, so I got to move things over a little bit. Good evening. My name is Pete Hermes. I've got a brief presentation on carbon stars, a lot of it rooted in a recent completion of the Astronomical League's Carbon Star Observing Program, which was kind of interesting, kind of fun to do. I think often, we always look for things in the sky that provide some interest or also provide a unique vision or look, I guess. For some of us that, especially under 8 inches of aperture, being unable to pull in, the fine detail on galaxies and nebula. We're stuck with a lot of stars and the planets, but still, you don't get that detail on the planets. But for the most point, of course, when we're looking at stars, they're point sources. We aren't going to see much more than that, other than occasionally we can see a little color in some of these stars. And ostensibly, most of the carbon stars are red, and I'll discuss it, or different shades and hues of red, and I'll discuss that. But that's what drove me towards this, completing the AL's program, and some of the things I learned from it, and I wanted to share some of that. And as usual, it's always a privilege and a pleasure and honor to present for you all. On the opening slide, you see probably one of the more well-known carbon stars or red stars, colored stars, La Superba, which is why Canum venaticorum, that's pretty readily seen. I think I'm trying to remember. I think even in binoculars, this will show up for a lot of folks. Even 10, for sure 20s, but I think even in 10-power binoculars, this one will show up. Anyhow, come on, let's go. Oh, I know what I have to do. Click. There we go. Okay, so just in a matter of introduction, I'll talk a little bit about the definitions and some of the characteristics that are specific to carbon stars, how they form, or at least what are some of the mechanisms. I'm not going to get real down in the weeds on this one, trying to keep it so that I understand what I'm talking about. A little bit about the classification, protocols, and procedures for carbon stars. A few things on observation here again, attributed primarily or focusing primarily on, how to see color in the stars, or at least the stars that manifest with some color, some of the things that can be done so that you can appreciate this aspect of viewing. A little bit about here again, the Astronomical League's Carbon Star Observing Program. And when I have a few examples, and you'll see that after when we get into the observation, you'll see some of my a couple of excerpts from my log, and you get an idea of what I did towards completion of the Astronomical League program. And then, of course, references and questions or comments will be more than appreciated at the end. If I make a faux pas or there's something really, I say something really wrong, please stop me and speak up and let me know what it is. We'll fix it and move on. Okay, as far as a few basic characteristics of carbon stars, for the most part, and like I say, there are always exceptions to the rule, but for the most part, and just about in all cases, and surely some recent discoveries or some discoveries to come in the near future may provide some additional information. But for the most part, most carbon stars are variable stars. They're late type red giants, most often, not always, but generally is the case. And thereby the name carbon stars, the reason being is because they have excess amounts of atmospheric carbon molecules, typically seen through, spectroscopy used to look at these stars. I mean, yes, we can see the color, but as far as looking for the lines specifically attributed to some of these elements and some of these molecules, there's elemental carbon, carbon monoxide, cyanogen, methylidine, and zirconium oxide. And those are the predominant molecules that present in carbon stars and thereby present with their basic coloring or hue. For the most part, carbon molecules will act as a filter, limiting the wavelengths, blocking those at the other portions of the visible spectrum, the yellows, the blues, and greens, however, allowing the reds to come on through. Here again, longer wavelengths like orange and red are going to pass through the carbon star. If you want to call it atmosphere, I mean, stars for the most part do have atmospheres, a little bit different than, what the planetary bodies might have, but they do have, the area immediately surrounding the star. High levels of carbon monoxide, utilize most of the oxygen. So thereby, there's going to be low, which may result in low concentrations of elemental oxygen, elemental carbon in some cases. Typically, there are two main methods or mechanisms by which carbon stars generally exist. One is you have carbon dredged up from the core by convection, which is merely matter or material towards the core of a star or deep inside of a star. Because it is hotter and lighter, generally it will move up towards the outer surfaces of the star, up into the atmosphere. Mass transfer between binary classical carbons and main sequence or dwarf companions is another. These are the two main mechanisms. You'll see they're referred to, and I'll talk a little bit more about that. The classical, which is carbon dredged up from the core by convection, and then mass transfer between a binary system where you have a classical carbon and main sequence or dwarf companion. And basically that larger star is pulling, of course, from the dwarf or the main sequence. With respect to what's going on as far as it's kind of hard to nail down any history, but for the most part, carbon stars, and they weren't necessarily called that immediately, but basically they were first discovered as what was referred to at the time as a Type 4 star by Father Angelo Secchi, who was a Jesuit and was did most of his work in Italy, a lot with some of the Vatican science outlets and some of the observatories that were available at the time. And I think just about all of his work was on the Italian peninsula. But for the most part, there are numerous papers that have been written. There are numerous people that have worked looking at carbon stars, maybe even specializing or focusing on that. But generally, you don't see too much of an attribution with respect to certain individuals. There doesn't seem to be any one researcher or astronomer focusing on research work in carbon stars. Going back to the classical carbon star, with regards to formation, like I say, atmospheric carbon, core outer limits by convection. And typically what you see, and there are two types, they have the CR and the CN types. You'll see some helium fusion, and the diagram is pretty simple and self-explanatory for the most part, but you have two helium atoms or nuclei that come together, they form beryllium. And then you see beryllium forms with another helium nuclei, and then we end up with the carbon. And this is what's referred to as the triple alpha process. Basically, the helium nuclei, if I remember correctly, is what's considered an alpha. And for the most part, we're not worried about the electrons here. We're just concerned about the nucleus of the atom, because that generally, you may have different ions, but that generally derives, the characteristic elemental components of any given substance. And so you can very easily see two heliums combining and then beryllium combining with helium to form a carbon atom, which is about halfway along the sequence of elements that are created in normal stellar processes, Typically, we don't see anything up through beyond iron, which is what, 26, I think. So this is not quite halfway through the periodic table to that point, but they are fairly common. And one other aspect, especially with respect to classical carbon stars, is generally they're longer period variables. And you're going to see there's a little bit of variation. There are some differences in the periods of some of these variables. But for the most part, you'll see these classical types are of the longer period. I would say in excess of probably 50 days on up into 5 years. A lot of them you will see are probably in the, I'm going to say, probably in the 100 to 300 day range, approximately. And of course, there are higher and there are lower. As far as the non-classicals coming back here, again, it is a mass transfer in a binary system of a classical carbon star, main sequence or dwarf. The main sequence or dwarf becoming, I'm sorry, I had that backwards. The main sequence or the dwarf becoming the carbon star. Okay, not the larger main star in the system. These typically have the classification or designation CJ and CH types. In some cases, these is where barium stars will sometimes come. The non-classical formation of a carbon star could result in a barium star. And these are also referred to as extrinsic carbon stars because one star is drawing matter from another one. In other words, external to its system, where it only makes sense intrinsically in the classical form, you actually have that carbon being dredged up from the central or lower limits of the star. Now, this is where I lose part of my slides. Oh yeah, for the most part, most carbon stars are classified in spectral class C. C system replaced the earlier Harvard R and N classifications, which is what they were known as probably in the earlier parts of the 20th century. However, you will still see some designations that will hold on to the previous classifications, but mostly most of the carbon stars are going to be classified CR, CN, and CJ, as I previously referred to, especially with respect to their distinctive coloring. Okay, as far as viewing, taking a look at carbon stars, actually observing them for the most part, color sensitivity is a problem at night for most of us, and especially those of us who are a little bit older. Oh, that I wish I was a little bit younger, because even though the problem would still exist, it probably wouldn't be as detrimental as I experience now. But basically, when we night adapt, we're setting our eyes up basically so that we're sensitive to, the least amount of color change. And of course, we try to avoid those bright lights so that we have the opportunity to be able to resolve and see with some degree of clarity the objects we're looking at through the eyepiece. Well, what this results in is a little bit of a detriment with respect to being able to perceive colors. For the most part, our color vision is diminished when we're night adapted. In some cases, that's a good thing. In other cases, it's not, because certainly if you're looking at colored stars, that's not necessarily a good thing, because you might miss some of the, especially some of the more subtle aspects of some of the colored stars, carbon stars or even blue stars for that matter. And so certainly, in some cases, it can be resolved by having, looking at some low light and actually reducing some of the night adaptation so that you're able to make those color perceptions. Not really recommended if you want to be able to, pick up some of the fine detail or, strong clarity in the objects you're looking at. But what it does do is it does bring out some of those colors. Typically, when I was observing, if I was having a problem detecting the hue from a particular star, it's not that I'm necessarily going to blind myself with a bright light, but I might look at a light off in the distance that wasn't necessarily blinding, just to reduce some of that night adaptation and try to return some color sensitivity where I get a little bit more rod base, which is what picks up the color in the on the back of your retina, getting the rods to work a little bit more, which they don't generally work as good. If you notice, when you're looking at things at night, ideally good, night adaptation, you're able to pick out objects with a fair amount of clarity and see detail and contrast But what you do lose, and even when you're looking at things of what outside of a eyepiece, and not necessarily observing through a telescope, is that often you will have problems detecting colors. And of course, here again, it's one of those things, as we age, that's one of those things that degrades a little bit more than most people. So, and this is why it can be a little difficult. These are one of the, colored stars are some of the neatest things to look at, but it does take a certain amount of effort with respect to night adaptation. Now, don't get me wrong, some stars, carbon stars included, some blue stars, they still show up regardless because they have a good solid color. They're not, especially if you don't have a faint one. Generally, the brighter the star or the more contrast that's available in your field of view, generally the light perception is going to be better. Okay. And of course, the fainter the star, the more difficult it becomes, to the point where, in some cases, and I know I was looking at a very red star, but I'm just not picking it up. Like I say, a couple of the things I try to do is, reduce a little bit of my night adaptation, or one of the other things, I tried was, just look, like I say, reduce some of that night adaptation by looking into a light, even increasing the magnification. Although I found, in some cases that worked, but not in all cases. Just trying to pick out a little more detail, because unfortunately, trying to increase magnification would reduce my field of view and therefore reduce the contrast that I might have in a field of view in order to see that color. So it certainly helps a lot if you have other stars nearby to help you, perceive those colors, because sometimes it can be very, very subtle. Sometimes not necessarily the case. You look at something like La Superba, that's not a problem trying to perceive that color. And of course, there's no set, color. You take a look at this color diagram, the different hues that carbon stars will come in, and they will run the whole gambit. I think typically, when you look at this, you're going to see, reference red certainly is attribute that you'll see assigned to carbon stars. Crimson, garnet sometimes. A lot of these other ones, not necessarily. They're varying level. Scarlet. You might see 4 or 5 of these attributed in descriptions, and certainly it's something that the Astronomical League uses in describing some of the objects that are included in their carbon star program. But for the most part, clearly about 15 or 6 of these, you don't see them referred to so much. They're just varying hues, but it is a way in order to be able to, assign at least some level of redness, I guess is the best way to put it. And in a lot of cases, it isn't necessarily always red. I mean, some of these carbon stars will appear orange, in some cases distinctively orange, although that is difficult to pick out. And especially in some cases yellow. But remember, typically carbon stars are going to restrict or diminish those wavelengths of light from getting through, so they can be rather difficult to pick out at times. I want to go back. Yeah, this was the second item on this slide. I just went back one. You'll notice I always put my personal phonetic soundings for these words, but the Purkinje effect, which deals with that luminance sensitivity shifting to the blue end of the spectrum in low light. Reds appear darker than other colors, and that's another thing that will happen with respect to becoming night adapted or trying to see color at night. Certainly, that's an issue to be taken into consideration. So moving on, here's a couple of examples of some probably real well-known carbon stars. I think most of you have probably seen these. For the most part, a lot of these, in some cases, are even visible with the naked eye. Most assuredly, like I said, through binoculars, but through a telescope, even low power, they're rather interesting things to look at. Heinz Crimson star. This was discovered, in the middle of the 19th century. By J.R. Hind, thereby its name, but it's a well-known variable, very popular. And you'll see the 5.5 to 11.7, that's the variation in the luminance of this particular star, and the period running anywhere from 418 to 441 days. It's 1,350 light years from our solar system, and the luminance of this particular star is almost 6,700 times that of our sun. Well, nothing far-fetched to really gather here, because you remember we said most of these super red supergiants or red giant stars. And of course, you'll see a rather low temperature for this, given the nature of this particular star. Just, it's under 3,000 Kelvin. This is basically the same slide. You can see here, this was my observation of this particular star that I did for the Astronomical League's Carbon Star program. Some of the notes that I'd put into it, Doug's seen this before, trying to identify some of the other stars. There were a lot of, dimmer stars in here. And actually, I mean, this color by itself would have shown up fine just by nature of this particular star. Like I say, some of the fainter ones were a little bit more difficult to perceive, the variations in the hues. This, I think, if I remember correctly, like I say, it was distinctively not so much, there was that crimson color, which is sort of like, it's not that deep dark red, but something a little bit brighter, I guess is the best way I can describe it. U Cygni is another one. And the interesting thing about it, and the reason I included this is because you'll see it's in the upper left-hand portion of this particular photograph. There's actually an 8th magnitude white star just to the upper left of U Cygni. And so it's kind of interesting. That helps bring out, to me, I think it brings out that color, or it's easier to see because you have some contrast. Now, I will tell you, of course, and you'll see it because I have my sketch of this. Of course, I didn't see this many stars, and this is I mean, it's a wide field, but still there's a lot of detail in there. I think I picked up at most 10 if I have that many. But here again, we have a similar star with respect to the variation in its brightness, roughly 6th magnitude all the way up to 12, similar to Heinz 463 days period. 32.6 light years away, only 10 parsecs, so it's relatively close. The luminance in this particular star is 368 times that of our sun. A little bit hotter, 38, just under 3,900 Kelvin. But when you take a look at this, and of course, I want you to make sure that you pick up the similarity between this photograph and my sketch. Not really, but you'll notice here again, the brighter star, which is actually, of course, it's blocked for me, is SAO 49479, and that was that 8th magnitude star. And you can see I have probably about 10, I don't know, 7, 8, 9, 10 stars in here, but this color was relatively easy to make out. One of the things I also included here was basically just my summary. And, typically the way I would put together my observations for this particular program, the little, the nice formatted 7-line summary of the particular object, where it was viewed, date and time, of course, what it is, what sort of equipment I used, of course, transparency and viewing. And here's another thing too that I didn't really mention. Transparency and viewing contribute a lot to how well you're going to be able to see whether or not it's if it has any color at all, and then being able to distinguish the various hues in some of these stars, especially as they might be described. One of the things, and I'll bring this up now, Astronomical League puts together, they have a nice guide, and it's something that they have to purchase. And this was a no-brainer for me. Of course, it's only about a $10 or $15 item, but it had a lot of good information about this particular program and what to do so that you could get the most out of it as far as being able to complete the program, but also enjoy the viewing that you were doing. And of course, the last item I include is power magnification. But going back to transparency and seeing, it goes without saying, as with just about any object you look at, you're going to be able to see it better, pick out those details, pick out the color better, of course, when you have, better transparency and good seeing conditions. If you have a little bit of wind affecting your seeing, or, the atmosphere is a little bit unstable, and then most assuredly, if you don't have a good dark spot, or you've got a lot of light pollution, or you have something else obscuring your vision, of course, that's going to diminish the experience you're going to have in this particular case. Finally, another example, this isn't something I looked at, but it's kind of interesting how some of these will show up in this case. Musefi is pretty much, there's a lot going on in this particular photograph here, but it gives you an idea that sometimes you can be looking at some of these red stars. And of course, this is, Herschel's Garnet star, another very, very well-known red star or carbon star. Here, the variation isn't as great. It's only about 3.5 to 5 magnitudes, but a significantly longer period, 860 days, plus or minus 50, 2,800 light years away. Very bright star. Estimates of luminance anywhere between 283 and 340,000 times the luminance of our sun, and probably medium range for most carbon stars, 3,540 degrees Kelvin. But you can see there's a lot going on, and this is a very wide field photograph of a lot of the surrounding area. But just to show that in some cases there are carbon stars that will sort of sit out there by themselves, and if they're faint and you have to use a fair amount of magnification to sort of pull them in, you lose a lot of the field, which I think, if anything, and it's probably true of any colored stars, but I think it's just as true of carbon stars. You get a little bit more out of them when you can view them with other stars in the field. Fainter or brighter makes no difference. I think it helps, for one thing, I think it helps bring out some of those colors. A couple of things about the Astronomical League's program. Like I say, I showed you the guide. I think it's all of about 25 pages, but it has a lot of good information explaining carbon stars. Of course, they have their list. I'm trying to remember. I think the program, as is typical of most Astronomical League programs, calls for one to view. Oh, wait, there weren't that many. No, there's more than that. 28. I'm trying to remember the numbers on it, but it escapes me right now. No, there were 100 objects in the program, so you go through them. But the neat thing about it too is, the Astronomical League and its guide. You can see I'll just show you a sampling of this. A number of their pages will have about 6 or 7 of the objects, and they provide a very good description, location, coordinates for it, and a description. And certainly, like I say, sometimes it was disappointing because I wasn't getting the same. I wasn't able to view the same thing, and so. But in a lot of other cases, it's kind of interesting when you see it and the color really stands out. It's kind of fun to do. But anyhow, like I say, there's 100 carbon stars. They range in magnitude from 4.5 to 13.9, and of course, this is varying throughout that time. Most are in the 7 to 8 range, so I think they're very accessible with respect to. I think I did most of these with my 5-inch reflector. I did a few with my 8-inch SCT. But certainly, of course, the darker the conditions, the better. And I think for the most part, I did just about all of them on my back deck at the house. So I don't have the darkest conditions, but they're fairly dark. I mean, as Doug has told me, the Milky Way, depending on the right nights, is generally visible from my backyard. But in some cases, I still have a lot of neighbors that like to keep their garage lights on. But anyhow, I'd say periods ranging from 2 to 600 days. So, in some cases, and I noticed this, especially with some of the shorter term stars that had a wide range, you can see these. I picked up on a couple of them, not most of them, maybe 2 or 3 of them, where I'd look at them, maybe 10, 15, 20 days later and recognize or remember a variation in the brightness. Not too often, though. Wider ranging carbon stars, yellow to orange. Generally, you're going to see the reds at the minimums. That's just the nature of these particular stars. Stars will appear redder as observing time increases. So sometimes, spending a little more time at the eyepiece, averted vision, but avoiding the light unless absolutely necessary. The quick glances, these are some of the other tricks that are used, that we all use to try to bring out a little bit of detail, especially color, with respect to some objects. Those are my references. Oh, I always put this in there, but you'll notice, you don't see the, typically, most of the carbon stars are going to be AMs way over on the right side of the Hertzsprung-Russell diagram. Probably a little bit up as far as absolute magnitudes. Here again, that's going to vary. They're variables, so they're moving up and down, but pretty much in that M range and a little bit more to the right. Thank you very much. Are there any questions, comments, or otherwise?
Quick comment.
Yes, sir.
We have that carbon star observing guide in the library.
Oh, very good. Yeah, if anybody's ever going to do this program, I'd recommend it. I think it makes it a lot more enjoyable to have the guide do it. You could do it without it, but I got a lot more out of it that way.
Thank you, Pete.
You're welcome. Let's see. I will stop. Actually, can't stop, can I? Thank you, Ross. Thank you, Steve.
Somebody.
Oh, stop share. There we go. Okay.
Before we move on, did anyone see the image that came out this week of Uranus from James
Sure.
Webb?
Yeah, it was great.
And continuing on. Okay. So next up on the list, we're going to be talking about Edward Barnard. He is an American astronomer and one of the first really heavy photographic astronomers, which we'll see more about this. He was born slightly before the start of the American Civil War in Nashville, Tennessee, in 1857. His father died about 3 months before he was born, and he was raised primarily by his mother, along with one other brother, which I could not his other brother was kind of an enigma. There's not really much that I was able to find on him or about any of his immediate family relationships. But what was known is that the lack of having a father figure around the house contributed greatly to the family's poverty situation. They were constantly impoverished for most of Bernard's childhood and teenage years. And his mother was also had a variety of constant health issues, which weren't really detailed. They were just summarized as quote unquote health issues, which could have been anything from what I haven't seen. So this constantly put them in a really tight spot. What's also interesting here is there wasn't, despite growing up in Nashville, Tennessee, there isn't a lot of information showing how the American Civil War might have impacted his early childhood, considering that I think Nashville was one of the cities that was raised by Sherman or had several battles near it. So I was surprised not to find much about that event on his early life. But what is known is not known, believed, is that his first exposure to astronomy occurred when he was about 4 years old, where it is believed that he saw the Great Comet of 1861. And this was one of the several events that would contribute to him gaining a lifelong interest in astronomy. He was not schooled. He dropped out after 2 months of the Nashville's public school program, just couldn't stand it. And I believe also some other situations with his family contributed there. Despite that, at age 9, he took a job as a photographer assistant, hoping to help get a little bit more money to help out his family's poverty situation, with a man named John H. von Strovoen. I butchered that, but I apologize. Curiously, though, this isn't your normal type of photography job. He operated as a guider for what's known as the Jupiter solar camera. And I have a picture of that on the next slide. And so he was basically like how we commonly use in photography, another camera to keep track of stars so that we can make sure the telescope remains on target. That's basically what he did, except he did this for solar observations. And just during his time on the job, he would also assembled a series of observational records that he used to discover on his own Analemmas, which Doug is certainly familiar with, which is the shape. It's a figure 8 shape that is traced out by the sun as it moves across the sky. If you were to photograph or if you were to look at the sun at the same time of day every day of the year. The next major event that contributed that astronomical event that really pushed him in his way was the partial solar eclipse of 1867, which passed directly through Nashville, which he saw at the age of 12. So here on the next slide, I need to figure out how to turn off subtitles because that's distracting. There we go. Sorry about that. This is a picture of the Jupiter solar camera, which, as you can see, is quite big. It's kind of curious that something of this large existed in Nashville or was still left standing after the American Civil War, because this would have been 1866 when he started this job. So only 2 years at most after the Civil War. So it's kind of curious on that. So outside of after his stint at this at the photography shop as a photographer's assistant, he was around 19 years old when he sought out astronomer Simon Newcomb when by chance the American Academy of Advancement of Science was meeting in Nashville that year. And he sought him out, was expressed, hey, I have this interest in astronomy. Is there anything that you would recommend? And Newcomb told him, go learn math, which with most of us, you can imagine, I don't want to go learn math. I want to look at things. And he came out of this meeting with Newcomb, by some accounts, very disappointed. Others said that he was enraged, and kind of viewing Newcomb as kind of like this paparazzi star from his point of view. But he didn't let that deter him. And shortly after that meeting with Newcomb, he went out and he bought his first telescope, which I think it was a right there. It was a 5-inch refractor, which he bought out of Pennsylvania, and coiningly referred to it as his quote-unquote pet. Kind of a weird moniker to add on to a telescope, but I believe some of us kind of feel the same way about our own equipment. So during this time period, after he purchased this telescope, he discovered a variety of things, mostly comets. He was a very good comet hunter. His first one he found in 1881, but he never actually formally announced this particular comet discovery, so it didn't go recognized, I think, until like very late in his career. Fortunately for him, during this time, really a wealthy New York businessman named Hubert Harrington Warner announced an ongoing prize of $200 to every person to every discovery of a comet that was brought to him and was proven and validated by other astronomers, which in the 1880s is quite a lot of money. So there was some comments that suggested that Warner was actually kind of an early fan of Barnard's, and this award was kind of set up specifically for him. Wasn't quite clear on how that might have been the case or how the two would have interacted before this, so I'm not quite sure about that side. But during this time period, over a span of 2 or 3 years, he would go on to discover 15 comets, and he would use the money to build a house for his wife in Nashville in 1881. Sorry, his wife, who he married in 1881. We won't go too much into external family relationships here. So there wasn't a lot. It was, from what I gathered, it was a normal marriage for that time period. And they had no children. So after this, messing around with his own telescope, finding a slew of comets to his name, his abilities of finding these drew the attention of a lot of local astronomers within Nashville. And they, out of the goodness of their hearts, which was actually really cool, is the amateur astronomers in Nashville funded him a scholarship so that he could attend Vanderbilt University. And the university, seeing all of this to him, also contributed him a job at the Vanderbilt Observatory, which he used to, him and his family actually lived on the observatory grounds. Him and his wife lived on the observatory grounds in the observatory warm house during this time period. And he would go on to take various courses in math and language the whole time. He kind of continuing the theme of not really liking school whatsoever. He never finished the degree. But despite his accomplishments, despite him dropping out of the degree, Vanderbilt would go on to award him what remains today its only honorary degree, which is actually really cool, considering it's like a 200-year-old university at this point. So after Vanderbilt, So during his several years at Vanderbilt, I think he, 83 to 87 was when he officially left. So over a 4-year period, he discovered a couple of prominent objects. There's a lot more in here. Just some of the ones that we might recognize. Was he discovered what's now named after him, Barnard's galaxy, which I don't have a picture of handy. He also discovered the California Nebula. Excuse me. And he independently rediscovered what's known as, I'm going to butcher this because it's German, Getzenschein, which is a similar cousin of zodiacal light. It's similar in appearance, but there's the physical aspects of how it gets generated are different between the two, but we won't go over that here. The light was originally first noted, like 1678 or somewhere around that period, by a sailing astronomer, whose name escapes me because I forgot to put it on the slides. And over on the right, there's a quick picture showing what it looks like. It's this bright band in the sky here over the ESO Observatory in the Atacama Desert. So, finishing up his time at Vanderbilt, he was reached out by the soon-to-be director of the Lick Observatory, Edward Holden, about a job. The observatory actually hadn't been built yet. He offered him a job anyway, and it was a salary of about $1,200 per year, which I quite well for that particular time period. And Barnard and his kind of really impulsive of him and kind of shocked that he got away with this. Basically packed up his whole family and moved to the observatory site before it was finished. So he left behind everything in Nashville and just said, "We're going to California." And kind of hurt him in the long run because since the observatory hadn't been built yet, he didn't have a job, and he struggled over the next couple of months to pay the bills, so to say, and would go on to spend a lot of his time just offering his services to copy legal documents in order to just buy food and other things for him and his wife. But once the observatory is finished, he thought, hey, I'm going to get to use some really cool equipment, blah, blah, blah. But he kind of got into several spats with Ed Holden very early on. And Holden was kind of spiteful and kept Barnard from looking at all, using the more powerful 36-inch telescope that was built in the observatory. And it basically was forced to use the 12 for a lot of his early work here. This would last for, I think, 3 or 4 years before he finally got on the 36-inch. But it didn't stop him. Using the 12-inch telescope, he did a lot. He photographed. He he photographed the first comet to be found using solely by photography. This wasn't a visual comet, but photographic, and he discovered this in 1892. He also discovered Jupiter's moon Alethea during that same year, which would be the last of Jupiter's moons that was discovered without the aid of a camera or other instrument. Excuse me. But in addition to that, he also, and I wasn't quite sure where this eclipse was because I forgot to look it up on the map, was simultaneously operating multiple cameras and photographed, this is the second photograph of a solar eclipse. There was one earlier than this that was recorded off of Africa, I believe. And this picture of the solar eclipse actually earned him a second honorary degree from the University of the Pacific over in California. So no verbal scolding, and people just gave him 2 free PhDs. So after that, after getting over his spats with Ed Holden and finally getting some time on the 36-inch, about a year later, he was offered a job at the Yerkes Observatory in Chicago, which is where he would spend the rest of his time before he eventually succumbed to various illnesses. He originally went there as a tester for the observatory's 40-inch telescope, but ended up, they just invited him on and he stayed. What was also really cool is that Yerkes would end up building a telescope solely for his use, which is a 10-inch what's known as the 10-inch Bruce telescope, and this would be dedicated solely for Barnard to use with photographic astronomy. So this led to a lot of really cool things, having this dedicated wide field telescope, which was necessary for photography because your auxiliary cameras are not very sensitive at all during this time. He contributed many images of Mars that were used to refute Schiaparelli's Martian Canal hypothesis, which much to the dismay of James Lowell later in the 1900s, because as for those who may not be aware, James Lowell built Lowell Observatory here in Flagstaff, Arizona, specifically to find these moon canals, Martian canals, and they were mostly figments of someone's imagination. He also, using the Bruce telescope and in collaboration with another astronomer in Germany named Max Wolf, photographed what became the first images of the Milky Way's central bulge and galactic disk. And I did not, unfortunately, have a year for when that was published. Some other discoveries that he also would do photographics. Forget the term for it first. Measurements of the proper motion of what's now known as Barnard's star. This is a small red dwarf star. It's one of the closest stars to Earth. But what sets it apart is that it has, with respect to Earth, this is kind of difficult to phrase, it is moving across the sky incredibly quickly. So you can actually see this whole, if you went out to the star every night over a 3-year period, you could see this star just move. I think it's like 0.2 degrees or something like that. No, 0.2 arc minutes.
I thought it was 10 arc seconds a year.
Thank you. Which is about 0.2. Never mind. My math is hurting. I need to stop thinking about math. In addition to that, he also photographed Halley's Comet, and was the last person to actually see the comet. He actually followed the comet about a year before it became visible. This was when the comet was still out near Jupiter, just kind of picking up. And he followed it all the way in and out of the solar system, and was officially the last person that would see the comet until it would return in 1985, excuse me. He would also go on to assemble a pretty big catalog of about 349 other nebulas with the Bruce telescope. Some more prominent examples of these are Barnard's Loop, which is this giant stream of gas that's hanging off of the big side of Orion. The Horsehead Nebula is also part of this catalog. It's known as Barnard 33. So there are a lot of objects that are here. Most of these would be very much photographic objects, not necessarily things that you would be able to see easily in a visual telescope. But this catalog was published by the university after his death. Which leads us to the end of this presentation of exactly how he died. So he was diagnosed with diabetes in 1914, and which lacking blood treatments nowadays was very difficult for him to deal with. His wife Rhoda would die of a stroke about 7 years later. During this time, she died. No. And sorry, losing my notes. And by some accounts, the loss of his wife devastated him. He kind of changed a lot after this, even though he wouldn't very long. He became very internal. But undeterred by his wife's death, he would go on to do a couple more key observations. His last scientific observation was an occultation of Venus by the moon, which he observed in January of 1923. And he would then go on and die from several complications with heart failure and diabetes in his home in 1923, where he is now buried in back in Nashville. And that's it. Those are some references. Any questions?
Yeah, would you go back to your first slide?
Sure. Let me. This one?
I don't know.
Or do you want the
very first one? Your really first slide.
This is my first slide.
No, that's your first slide. Okay. Okay. Never mind.
What's
Nothing.
Okay.
Just
were you thinking you saw a typo or something?
Yeah, I thought I saw a typo. I thought I saw the name spelled Bernard, and I was saying, oh, wait a minute, I thought it was BAR. Okay, never mind.
That might be in there somewhere on accident. That did kind of flip flop his names a couple of times, but thanks.
That's okay. Don't worry about it.
Okay.
So, Connors, Pete, I got a question.
Mm-hmm.
So, in your readings, and I know you mentioned a little bit with respect to Mr. Barnard, do you think it was a general, allergic reaction to education, or was he just, he didn't see it as necessary to accomplish what he wanted to in astronomy, and he'd just as soon continue on with his observations or the work he was doing?
I think he just didn't have the patience for it.
Oh, okay.
Yeah, that's what I always read about him, is he was very thin on patience. And also he had a, what today I think you'd call the opposite of an inferiority complex. He thought he didn't need it.
Yeah, because it's kind of surprising. I mean, basically, he had almost a 55, 60-year career in astronomy.
Now, one thing I will say, Connor, I don't know this for sure. Those 2 honorary degrees that he got, one from Vanderbilt and one from University Pacific, I'm not sure those were PhDs. I don't know if they were doctorates or if they were just honorary bachelor's degrees.
Honorary degrees are typically given as honorary doctorates. They typically don't. Most universities don't give out honorary bachelors.
At least according to the
Wikipedia article.
Was that true 100 years ago?
That, from what I briefly read, seems to be a general truth.
Okay.
It was considered a badge of honor to be given.
Okay, I just didn't know.
Yeah, it's a question. I was kind of confused about that too, because I was like, "What are honorary?" Because I've heard the term before, but didn't know, it's basically they give you a free PhD because you made a lot of special accomplishments.
Okay.
Like for example, Bill Nye has an honorary PhD and an honorary engineering PhD, I believe. Anything else?
No, good job. Thank you.
There's kind of also one thing I was, if you're kind of interested to learn more about the Jupiter solar camera, you're not going to get a lot of help with Google, but mostly because Jupiter and solar are very common terms, and so they don't turn up anything like this.
I'm looking at the camera and it looks like it's just a big projection thing. Like it's got the lens is up at the top left, and there's that big sunshade around it that puts the whole telescope in shadow. And then I'm guessing it projects the image down into that box on the right.
That would be my assumption as well. But I was kind of curious that they had an instrument this big in Nashville, and I hadn't heard about it before. But it was
Nashville was not destroyed by the Civil War. It was occupied by Union troops for most of the Civil War, and it was not part of Sherman's march.
Okay, that I was getting some things wrong.
Yeah, I think for the
It's
most
been
part,
a lot of the years that I've had history.
the most part, the Civil War was rather benign to Nashville. I mean, there were certainly some other towns in the region that took a lot more, but I don't, Nashville wasn't necessarily a strategic location.
Okay, I learned something new.
It's an interesting looking projection box. That's really strange.
Right? And I was disappointed that I couldn't really find anything about this except for presentations in which Barnard came up. So I couldn't find anything about why the telescope was built or what it was being used for other than to observe the sun.
Oh, you don't know if it was associated with the university?
I couldn't find anything about that.
Okay.
It seemed to have been a privately owned telescope because it was because Barnard was looking as a photograph assistant out of a corner shop, and apparently they were doing stuff with this telescope, from what I was able to see. But I couldn't find it. You can't find anything about this because the Jupiter solar and telescope, when you throw them into Google, they throw you to Jupiter or James Webb stuff, which is not at all helpful. So.
Oh wait, there's a guy inside the scope. Yes, there is.
Oh, you talk about that Louvre? Oh yeah.
Up above the guy who's sitting down, there is someone's up there in that top slot.
Does he have like a top hat on? He does have a top hat on. Gee whiz.
Yeah. So that probably continued where it's a giant projection box, and they probably had it a piece of paper or something like that in the back to draw observations on. Or
well, that's what I'm thinking is the projection is probably way down at the bottom right. But these are places where these slits in the side are perhaps places where you could go in and look at the projection. You want to be in a dark, and you can probably close those doors. Yeah, you can. Those are doors that you can close. So you can go inside the enclosure, it looks like, and then close all the doors so that you're in a pitch black environment, which gives you the ideal projection on that bottom wall. What a unique gadget.
Good catch, Steve.
So.
Really unique.
Right? And I was really upset I couldn't find more about this. So. Let me double check some things in the chat. Okay, nope, so things we've already gone over. Okay. So, and with that, that is it for tonight. Thank you, everybody. I do hope you, as a reminder, do go check out the bulletin. Let me know if you're interested in the solar filter workshop. Still actually looking for people that are interested, and I'm surprised I haven't gotten anybody yet.
It's early.
It is, but I need to go out and buy more of the materials.
Yeah, you probably won't get a lot of responses until like July. That's when people will start thinking about it. They'll start saying, oh yeah,